Welcome to This Explainer. Today, we're going to demystify the hidden rules, connections, and processes that let our digital and physical worlds seamlessly interact. We literally live in an era where data floats invisibly through the air all around us, gets caught by our devices, and can then be materialized into solid objects right on our desks. It's wild. But how does that actually happen? What are the underlying mechanisms that keep this whole thing from turning into total digital chaos?
Before we really get going, I want you to ask yourself something. Just take a look at the devices sitting around you right now. How exactly does a digital blueprint travel through thin air, bounce between cell towers and routers, introduce itself to your computer, and then physically manifest without the entire system crashing? It feels like absolute magic, right? But unless you've got a tiny wizard hiding inside your router, it's actually the result of some incredibly elegant engineering and universally agreed upon rules.
So here's our roadmap for today. We're going to start with setting the standards, then look at Wi-Fi versus WiMAX, move into plug, play, and UPnP, tackle hardware translators, and finally end up at how 3D printing works. Let's jump in. Kicking things off with Section 1, setting the standards with the IEEE. We have to start our journey at the absolute highest macro level with the ultimate rule makers of the digital world, the IEEE. You've probably seen those letters on the back of a router box or a spec sheet at some point. It's pronounced IEEE, and it's this massive organization of engineers, scientists, and tech professionals who literally write the international standards for how networking technologies operate. Take the famous IEEE 802 protocols, for example. If you've ever used Wi-Fi, you're using their 802.11 standard. Plugged into a local network, that's their Ethernet standard. Without them, your smartphone absolutely wouldn't know how to even begin talking to the router at your local coffee shop. And what's truly fascinating here is the sheer scale of this group. Out of their 533,000 members, spread across 190 different countries, over 69% are actually located outside the United States. It's proof that the standards making our internet tick aren't just dictated by one single nation. It's a truly global collaboration, a universal language agreed upon by the brightest technical minds on the planet. All right, moving on to Section 2. Wi-Fi versus WiMAX. So now that we know who sets the rules, let's look at the incredible scale of the wireless networks they govern. We'll start from the outside world and work our way towards your house. Look, we all know Wi-Fi is fantastic for local coverage. It's great right up until you walk 2 rooms away and completely lose your signal. But what if you need to provide internet to a whole town? Enter WiMAX. This stands for Worldwide Interoperability for Microwave Access, and it runs on the IEEE 802.16 standard. Think of it as a wireless alternative to your traditional wired connections like cable or DSL. It's designed to deliver high-speed, last-mile internet access. So while Wi-Fi covers your living room, WiMAX is built to literally blanket entire cities, rural regions, or massive corporate campuses. To really put the power of WiMAX into perspective, a single central base station tower can connect directly to users up to 50 kilometers. That's 30 miles away. You can pull a blazing 1 gigabit per second from a tower that is literally in another zip code. Whether you're using a fixed stationary antenna on your roof or a mobile setup, it delivers just incredible performance over stunning distances. Now for Section 3, plug, play, and UPnP. So we've established how signals travel vast distances from a WiMAX tower to your home router. Now, let's zoom in on your local home network and see how your personal devices actually introduce themselves to each other. Hardware plug-and-play is the reason you don't have to manually install sketchy software from a CD-ROM just to use a new mouse anymore. The second you plug it in, your operating system automatically identifies and configures it. UPnP, on the flip side, is the magic network protocol that lets your smartphone and smart TV instantly find each other over Wi-Fi. That's why you can effortlessly cast a video to your TV without ever touching a firewall setting or manually typing in a crazy IP address. It just works. Which brings us to Section 4. Drivers, our hardware translators. Okay, so your computer just downloaded a file over a massive WiMAX network, routed it through your Wi-Fi, and recognized a newly connected device thanks to plug and play. But how does the computer actually know how to command that device? Enter the driver. Think of your computer's operating system, whether it's Windows or Mac OS, as a manager who only speaks English. Now, imagine your hardware, your printer, your graphics card, your mouse, as brilliant workers who only speak French, Japanese, or Spanish. A computer driver is a highly specialized piece of software that acts as the necessary translator bridging that communication gap. Without a driver, your operating system might know a printer is plugged in, sure, but it wouldn't have the vocabulary to tell it to actually print a document. Finally, Section 5, How 3D Printing Works. Let's transition from all those digital handshakes into the realm of physical output. Let's see how those digital blueprints actually become real-world objects right before our eyes. 3D printing, also known as additive manufacturing, builds solid objects layer by layer. And every single 3D print goes through 3 simple steps. Step 1 is the digital model. You design your own blueprint or maybe download one from a community platform. Step 2 is slicing, which is a fantastic parallel to what we just talked about. The slicer software literally acts as another translator, chopping that 3D object into thousands of super thin horizontal layers and sending those specific step-by-step directions directly to the printer. And then, step 3 is printing. Armed with its translated instructions, the machine brings those layers into the physical world, melting material and stacking it from the bottom up until the object is completely finished. If you decide to get into additive manufacturing yourself, you're generally going to encounter 2 main methods. First up is FDM, or Fused Deposition Modeling. This is for sure the most common and affordable type of 3D printing. It works by melting a spool of thermoplastic filament and pushing it through a hot nozzle. Honestly, it functions a lot like a highly precise robotic hot glue gun. Next is SLA, or stereolithography. Instead of melting plastic, SLA uses incredibly precise lasers to cure and harden a pool of liquid resin into solid plastic. Because lasers can be controlled with microscopic precision, SLA produces highly detailed objects. It is the absolute go-to choice for things like intricate tabletop miniatures or complex jewelry molds. To wrap up this explainer, we've covered some incredible ground today. We've seen how global organizations like the IEEE craft the rules that allow WiMAX towers to beam internet across 50 kilometers. We've learned how UPnP and drivers help those incoming digital signals shake hands with the physical hardware right in our homes. And finally, we explored how additive manufacturing translates those digital blueprints into tangible physical reality. Considering this amazing journey from macro wireless networks all the way down to physical creation, I want to leave you with this to wonder about. As our physical and digital worlds continue to completely merge, what will the next invisible handshake look like? And what new global standard will we invent to control it?